Welcome to the demonstration how to work with the hydroponic formula calculator and analyzer.
This tutorial has been prepared to show in a simple way how to work with Vitaran HC. Vitaran HC is a software program designed to calculate and/or analyze nutrient solutions for hydroponic and other agricultural uses. Calculations are done using Microsoft Excel spreadsheet program. This software is suitable for all levels of user, hobby, commercial growers, researchers, in fact, any person interested in soilless culture. Minimum knowledge, limited to a few basic concepts of elementary chemistry, is all that is required to use this software. The advantage of using this program is the simplification of the mathematical and chemical calculations needed to formulate nutrient solutions. Importantly, Vitaran HC formula calculations take into account any mineral content of the base water supply. That is, the results will be customized to suit your water supply.
To get the very best out of this program, it is highly recommended that the user reviews some basic chemistry notions. Some of them are atomic and molecular weight concepts and some knowledge of salts, acids, alkali, and purity. Also, a basic understanding of conductivity and pH ideas is highly suggested. Now, let's get started. But, take your time in going through this demo. At most, only a bit of common sense is required. The sequence starts in calculator page number 1. As you can see on the screen, the supply water analysis procedure is very well explained there. After having the supply water analysis results, go to Insert Values page. Fill the blue cells on the chart with the corresponding figures. In the upper part of page number 1A, there is a small group of cells. One of them is blue. In it, the user can write their own conductivity measure in microsiemens/centimeter. According to the value written in it, an alert cell will be shown below. Let's see. A 0.35 microsiemens/centimeter of conductivity will show a green cell, suitable supply water for soilless culture. But a 0.75 figure in the blue cell, the alerting cell, will be yellow. Thus, some precautions will be necessary. And with a 0.95 number on the cell of the user conductivity reading, such cell will appear red and requirements of care will be increasing. In the calculator, there are several cells having a red triangle alert flag beside them. A message like is shown here will appear when the cursor is passing over or rests on such cells. Below, at the same page number 1A, on the left column corresponding to conversions, it will appear automatically the ions value of the supply water chemical analysis being in ppm or in millimols/liter as in according to with the software preferred by the user. These figures are coming from Insert Figures page. A final result balance now appears at the bottom of sheet number 1A. Along with this result are two indicator cells. You can assume that the lab test and results are okay if both the cells are sky blue, and you should now continue to the next step. In the shown example, the sky blue color in both cells reveals that analysis was correct for hydroponic purposes. Now, Let's continue. In our example here, the water is very slightly alkaline. Besides, the hardness indication on page number 1A displays that this water is medium hard, indicated by a green colored cell. When necessary, the pH correction will be done on the following page. We now move to sheet number 1B, where we have an adjustment of the base water pH. Note that at this time the pH indication cell is red. This means that an adjustment of the pH value will be required in order to bring it to an appropriate value for use in the final nutrient solution. pH modification can be achieved by using one of the three different acids. Select the acid to be used. Phosphoric is the preferred acid to use. Insert the figure 1 into the corresponding blue cell. Now automatically, the calculator will display the necessary amount of the selected acid, expressed by the weight or the liquid volume, needed to attain the appropriate pH. The calculation of the nutrient solution formula to suit your base water now starts here on sheet number 2. This sheet is the heart of the calculations. The first table on this page shows the mineral composition of the base water. These values have come from the figures you previously entered on the sheets number 1A and number 1B. Note, in this example, it can be seen that there is an alert red cell on the sodium ion. This was not indicated previously for water drinkability in sheet number 1A, since that level is okay for drinking water. However, the signal is very important for hydroponic nutrient solutions and could be a problem for some crops. The second chart on sheet number 2 allows you to insert the desired values for the final formulation. For normal conditions, select a value between the maximum allowable and minimum advised values. Obviously, extreme values could be used for research purposes. Each one of the blue cells must be filled with the appropriate value for the mineral shown. At least there are 4 options for the selection of the values for insertion into the blue cells. A. Use your own criteria to establish the maximum and minimum values as shown on the previous example sheet. B. Insert values into the blue cells taken from a known formula. C. Copy one of the suggestions from our sheet formulas. 2. D. Copy a historical formula from literature. See formulas. 1. You can copy and paste it into sheet number 3 and then transport the resulting values obtained to sheet number 2. Options A and B are obvious methods. Option C is a simple method. Option D will probably require a more advanced application. Let's see an example of the last case. At Formulas 1 sheet, for instance, you may select Dr. Cooper's formula number 1. Now, copy the selected column there and paste it into sheet number 3. The ionic results for this formula now appear at the bottom of sheet number 3. These are, in the center line, Dr. Cooper's formula ionic results. But, you should note, there is a value slightly higher than recommended. All the values at the line formula results must be copied into the blue cells of a similar chart at sheet number 2. Those values can be copied as follow. First, on the corresponding square of sheet number 2 insert the equal sign. Second, go to sheet number 3 and click on the respective cell and then press enter. Third, the program automatically returns to sheet number 2 showing the value number in its chart. Note the yellow alert cell indicating an out of limits value. Fourth, repeat the same procedure with the rest of the cells until the transfer of all the data is complete. Now the desired values for the nutrient solution, example Cooper's formula, are shown in the results section of sheet number 2. To correct this yellow cell, if you want to do it, a lower number must now be inserted, for example, 209. On this sheet, it is possible to add minerals not previously considered such as silicon, Si, or to make any other modifications, always modifying the values entered in the blue cells. Formulation values are automatically determined by reducing the ion count in the base water supply. In this example, 2 red cells display negative numbers. This means that there is an excess of both ions in base water. An indicator alert is located below on page number 2. It indicates that the water is unsuitable for hydroponic growing because, although there is an acceptable value of chlorine ions, there is a toxic level of sodium ions. Note: in order to continue with this demonstration, we need to work with acceptable water. To do this, we had deliberately reduced the sodium ions value of original water from 130 down to 46 ppm. The results are in the following table. Water still contains chlorine and sodium ions. But now, for demonstration purposes, we have reduced the sodium content. Note: no further amendments may be done here. If something is not acceptable, it will appear as yellow or red cells. In such cases, the review will be needed in the previous pages. Reference: blue cells. From here on, sheet number 4 regulates the whole calculator function. Water indicator alert, with the analysis modified for this demo, shows that this new water is good for hydroponic use. This next step asks you for the selection of the chemicals you want to use to obtain the balance of cations and anions required by the formula design. These selections can be made to suit the grower's preference and of course to match those chemicals locally available. This job starts at table number 1. At this point, one of the ions is selected as a head of all the series. Continuing with the same table. For this example, we decided on 2 things. The first one is to add all the magnesium as sulfate. Of course, the magnesium nitrate is gone. The second thing we decided was to add potassium as a mix of diacid phosphate, 26%, silicate, 10%, and nitrate, the rest to balance. The salts for the macro elements are all selected here. Below at the same page number 2, microelements selection should be done. In this case, figure number 1 is used to make selections. However, the selection done in the last screen is most appropriate for microelements. Each salt manufacturer may have different purity standards. If the values that are in the blue cells of table N2 don't correspond to the ones written on the labels of your chemicals packages, change the percentages here. The other cells will automatically change their values. Note: all numbers shown in this table will work in the calculator. They can be used for growers' own calculations. They are conveniently included in sheet number 5A for those requiring that kind of information. In sheet number 6 there are 3 important tables. The upper one shows the ionic contributions reached by the formula obtained. The second one displays the values really we wanted to get. The third one shows the differences between both previous charts. Red cells with negative values mean too much of that ion. A white cell shows we are short of it. The level of sodium and chlorine is low. It does not affect the example formula. Silicon is also inside limits. Studying figures at table number 3, and using common sense and trial and error shows that 2 values need to be corrected. First of all, in order to correct the nitrate amount, on page number 4 we change 100% the ammonium source. Thus, we passed from ammonium nitrate to ammonium sulfate. Now, watch what happened in the new table number 3. Ion nitrate was corrected. Besides, observe that ion sulfate is still smaller than designed. Let's continue. Now, at the macroelements selection chart, let's put 12% of potassium sulfate and 13% potassium silicate. Note the produced changes in table number 3. Besides that, we will be able to reduce ammonium in the formula at page number 2, modifying its amount from 17 to 10 ppm. Also, at the same time, we will raise calcium nitrate from 149 to 160 ppm. Remember that this salt always carries a certain amount of ammonium nitrate. As can be seen now on the screen, after these changes, table number 3 now shows acceptable figures. It may be necessary to make several trial and error operations in order to reach the final balanced values, i.e. a few more steps than those shown in our example. Each type of water, each formula design, the kind and quality of salts used, are all factors that can produce procedural variations. However, the use of basic criteria and common sense together with some trial and error in pages number 2 and number 4 are the way in which to reach your ultimate formulation. At page number 7, concentrated solution formulas are shown. They are called 100:1 stock solutions. In modern hydroponics, separate stock solutions containing all the plant's required ions are used. This is a convenient procedure since under conditions of high concentration certain ions can react between them, producing non-soluble salts. Precipitation of these salts will unbalance the formula. To avoid this problem, each one of these stock solutions has completely soluble salts. As we said, also appearing on sheet number 7 is the microelements intermediate solution formula, that is the trace elements solution, required to complete stock solution B. Once prepared A, B and C stock solutions, the last one if silicon is used, there are 3 options. These are: A. Using them according to dilution ratio 1:100. B. Use them further diluted. C. Use in a more concentrated nutrient solution. The selected option will depend on the variety of plant to be grown. In order to select it, on page electrical conductivity optimum ranges it is possible to know the conductivity required by many crops. First, let's see case A on page number 8. By considering to dilute equal parts of stock solutions A, B and C in 100 liters of water, it can be observed that the calculated conductivity of the final nutrient solution will be around 2400 microsiemens per centimeter. This is a good value to grow peppers, tomato, mint, melon, etc. The ionic final result showed now at the screen includes all salts used in the formula plus the original ions from the water supply. Case B. In this case more water is used. Thus, the final conductivity will result lower and the nutrient solution will be nice to lettuce, artichokes, garlic, thyme, between other plants. As we can see, now the amount of zinc is slightly lower than the minimum recommended. If it is desired to correct it, it is possible to do it raising its designing figure in page number 2. The final formula will change a little bit and zinc appears corrected in its ionic composition. Case C. If we want to grow beans, eggplants, cabbage, carnations, and many other plants requiring higher conductivity values, we need to use less water to dilute the stock solutions. We may observe the ionic composition on the screen. It shows that nitrogen as nitrate is higher than the maximum is advisable. Again, going to page number 2, the formula can be redesigned reducing figures of nitrates, ammonium, potassium, and calcium. This is the resulting effect of such changes. A cost calculation of all salts in the developed nutrient solution formula can be done here by inserting the individual raw material costs. Your purchase prices of chemicals used must be entered into the blue cells. Unitary costs calculation appears immediately. The total cost of chemicals per liter for this nutrient solution formula will be automatically calculated and shown at the bottom of the table. After filling the blue cells in the sheet called Summary with the required values, by pressing the corresponding button you can get a printed sheet of all your work to be saved in your files. This is the printed sheet you will be getting by pressing the previous button after you finish your work. I hope you like it. Vitaran HC has many more fixtures. Most of them are only slight variations of the same procedures as explained in this tutorial. The other fixtures will become obvious when you start to work with the calculator.